All right, excellent. So here we go. Welcome everyone to the second session of Machine Learning from Square One, where today we're going to be taking a look at word embeddings and classification and also some language modeling. So these are crucial topics in NLP because they lay the foundation for what can be done later on with more advanced modeling, but they all essentially use the same kind of game that is used here. That is, for instance, language modeling, which is what we're going to describe just now. Before we get into the details, I'm going to maybe describe a little more how the structure is going to work this session. The idea is that it's a little bit more interactive now. So really, if anyone has any question, then they should either put it up on the chat or raise their hand. And it would be great if they could ask it in person, like with their voice if they want to. If not, using the chat is fine. But the idea is to maybe explore these topics in a little bit more of a conversation and explore how the different parameters affect the models, how essentially exploring how to do some machine learning with some NLP techniques that we're going to describe just now. So if everyone's cool with that, we'll just hop right in. Now, as far as word embeddings go, this is a really interesting topic because this is sort of the first step in how an algorithm or any kind of computer can try and understand what the meaning of a word is. If you think a lot of how a word is represented to a computer, you would normally say, for instance, if you have this sentence, I like cats and dogs, for instance. If you imagine you're trying to tell a computer like how you can, what does this sentence mean? Or an example task would be, for instance, to retrieve similar documents. For instance, you would think that you kind of need to understand the documents to do this. But really what was done classically is where you essentially just search for the same words, regardless of if you understand the meaning or not. So for instance, if you're searching for a document, you would look for documents that have the word I and like and cats and dogs, and then you could get a list of documents back, and they might be related and that sort of thing. But the algorithm that's doing this doesn't actually understand the meaning of these words. It's just essentially using co-occurrences and that sort of thing. And so this is what word embeddings are trying to address. They're trying to address the fact that we're trying to figure out what it is that these words maybe represent in a more abstract sense. And we're going to use these co-occurrences in a slightly different way to essentially compute some, to put these words in a point in space. So in order so everyone can follow along, what I'm going to do is share this notebook so that everyone can like maybe look up and down as need be. Let's change this to anyone. Link. Copy. And I'll put this in the chat. Yes.
I think Francis is here anyway, but could you also put it in the Discord, please?
Yes, let's put it in the Discord. Let's see. I'll put it in ML General. There we go. Sorry, I didn't see the chat before, so good call. There we go. Chat is open now. So, this is essentially what a word embedding kind of, or what a word embedding would look like essentially. A word embedding is essentially a point in space. If you imagine, say for instance, you have a three-dimensional space, right? You know, you've got like something like this. These are our three dimensions. We'll actually use different colors to describe them. like so. So this is our sort of X, Y, and Z coordinates and that sort of thing. So essentially, if we were to put a point in space, say I don't know, this point in space over here, that would be sort of like down there and over here, and over here. Essentially, this point could be represented as, you know, 2, 1, and 0.5, effectively. So we'll separate these out. This would essentially be a 3-dimensional word embedding. And what this means is that this point in space can be clustered with similar words that are around it. So if we see in this graph, for instance, a refrigerator, oven, microwave, these General Electric, LG, these are all sort of clustered together. So you could imagine these as points in space, essentially clustered, similar together. Here, this is an example of a 2-dimensional word embedding. And if we've got 3D space, we can imagine 3-dimensional word embedding. And what we're going to be dealing with here are essentially 100-dimensional word embeddings. And they could be of any particular size. And so whenever anyone says something like an n-dimensional word embedding like this, embedding, what it means is just every single word is represented by an array of n numbers, which would be like 100 numbers or something. And so this is how we're going to represent these. So in PyTorch, one of the ways we can essentially represent a group of embeddings is by essentially we have this particular class that's called an embedding class, and we can specify certain parameters, and we're going to explore these right now. But essentially, one of the key things about vocabulary and essentially turning words into embeddings and having a unique sequence of numbers associated with these is the fact that they need to be converted. Each word needs to be unique in of itself. So for instance, I like cats and dogs. Here we have essentially 5 separate words where, and each one of these could have an associated ID. So that this could be ID, I don't know, 1, this could be ID 2, ID 3, ID 4, and ID 5. As such. And what this means is that whenever we want to do a lookup effectively for the word embedding of I, for instance, so we would essentially say would be like embedding, and then put in the embedding for the index of I for this particular embedding, and then the result would essentially be a vector containing that particular embedding unique to that word, and the same thing for all the others. And the interesting thing here, let's remove these. The interesting thing here is that this is exactly what this is providing us. So the embedding class in PyTorch is giving us first the vocabulary size, and then it's giving us the embedding dimension. So here we have 5 words effectively initialized randomly, 5 words initialized randomly, each with an embedding dimension of 8. And we might be thinking like, why there's this representation here that is essentially a matrix, and why is the representation of this a matrix? There's a really interesting reason for this, because essentially everything in machine learning or especially when it comes to deep learning and neural networks, everything is matrix multiplication or vector matrix multiplication. And essentially, in order to obtain the embedding of a particular word, all we need to do is a specific kind of vector matrix multiplication, where the vector is going to represent a one-hot encoding of a word. Now, I'll cover what a one-hot encoding is. Is essentially, we know we have these IDs over here, like 1, 2, 3, 4, 5, over vocabulary. And any sentence that contains the words that are inside the vocabulary can have an embedding associated with them. And the way we're going to essentially get the embedding for this is the way we're going to get this is by essentially turning this this ID into a one-hot encoding, which is represented like this. So really, we would have the index would start at 0 in theory, but for instance, for all intents and purposes, we'll just keep this. We'll assume there's another token over here that has ID 0, for instance. And so the index, the one-hot encoded vector for I would be 0, 1, 0, 0, 0, 0. In this case, where our vocabulary size is equal to 6 tokens, where we go 1 through to 5 over here. And so this one-hot encoding works, gives us this. And next up, if we've got the word for the ID for 2, for instance, this essentially gives us the second encoding, like so. We have a question. So why not one hot encode at a character or alphabet level? And that's a great point. So if people used to do this, essentially what it means is your vocabulary is then reduced to however many characters you have in the alphabet. And that means that the representation that you have, the representation, there's a lot more cost to representing these internally in the model, because essentially the model has to realize that groups of characters working together have meaning. And really it comes down to how you how effective these representations can be. So you could even have a word embedding that is representing a sentence, for instance, and this sentence could be unique, and the sentence could essentially represent. You could have so many different sentences, but essentially the vocabulary size would be enormous at that point, and you don't necessarily want to do that. So if we go back to the original stage where we're at with the one-hot encoded vectors and what this has to do with the matrix that we have here in the embedding, what we're going to use this for is essentially we're going to do vector matrix multiplication, where our vector here is going to be the one-hot encoded. Oh, this should be a 1. The vector is going to be on one side. So for instance, we're going to have our embedding matrix here. So matrix over here. And then we're going to have our vector over here. And here we know, so this will be like 0, 1, 0, and so on. And the interesting thing here is we're essentially going to have a 5 by 8, 5 by 8 matrix. This is going to go over here. Vector matrix vector. So 1 by 0, 0, 1 by 5 over here. These commute together, and the result of this vector matrix multiplication is essentially a 1. Oh my God, sorry. The result of this is essentially another vector that is a 1 by 8 because of these two. And because this is a one-hot encoded vector, what's happening here is every single row where there is a 0 associated to it, like this, is actually being set to 0. And the only row that we're keeping is the one that's associated to the 1 at this point, because essentially everything else is being canceled out. So this whole operation is just essentially selecting a particular row of the embedding matrix over here. So for instance, if we were taking if we had a one-hot encoding for, I mean, we can actually do this right now. So for instance, let's take this. We take an array torch.tensor, and we'll set this to be we'll set this to be a matrix, for instance, where it's a 0, 1, 0, 0, 0. So here we have a vocabulary size of 5, for instance, and then this is also vocabulary size of 5. And so we'll set this for 1 hot. And then afterwards we take our 1 hot, and then we do some matrix. Oh shoot. We do a matrix multiplication with the embedding rate. Oh, we have to represent this first. We have to start torch as well. And this should work in theory. This live coding. Put this back. Here we go. Oh my God, these particular types. They need to be the same type. So D type is torch dot 32. There we go. So essentially what we're doing here is we're essentially capturing this row of the matrix. So -264, and that sort of thing. And this is what these IDs, why these IDs are useful to us. And this is all that's happening inside these embeddings. We're just simply capturing these. So now that we have an idea of what an embedding is, we need to kind of figure out how to use these embeddings and what it actually means to sort of perhaps choose a particular word in a particular case. So for instance, one of the things we can do is play a game inside the model called, which is called language modeling. And this is how this is how the model is going to figure out where to place each of these points in space with respect to each other. So these, so language modeling in particular, what it means is, for instance, if we have the word, the sentence, "I like cats," and, or here we have a little typo, but we have the words, "I like cats," and the next word would be something like dogs, for instance. We would imagine that, but it could be anything else. It could be Mars, it could be French, it could be any other particular word that we have in our vocabulary. And the model's job is essentially to take this, to take all the context and figure out which is the most likely vector that could actually satisfy that particular sentence. And if you do this enough times, what's been found is essentially those points that the model actually gets really good at predicting the next word. This is especially what's been used for some of the newest models like GPT-2 and GPT-3 and BERT as well. And this is how they're trained effectively. They're just given a whole bunch of context, maybe like 500 words, and then they're given and then they just keep predicting the next word over and over and over again. And so we're actually going to do this later on. We're going to build our own language model. And really, I think what we're going, maybe the best way to do this, because this is sort of a topic that where a lot of things happen at the same time, in particular with language modeling, because we need to know embeddings, we need to know classification, we need to know a little bit about how to train these things. What we're going to do is sort of dive into the task, maybe in a more broad sense, and describe it. And then I'll go into details of what the model actually looks like and how we're creating this data set. So what we're going to do broadly is essentially we're going to use this text right here. This is just some poetry, some old English poetry, and we're going to separate it. We're going to split it by spaces, essentially. So if we take a look at the words that we have over here, let's just take a look at words. And then like the top first 10 words. When 40 winters shall, blah, blah, blah. These are essentially going to, these are going to form part of our vocabulary here. And once we do this, so for instance, if we set this Over here, just like we described before, we need to take the IDs of these words. We need to take words to IDX. And this is just a dictionary that is essentially going to map from one word to another. Lots and lots of words. There's around 100 words in this text, so this is going to form part of our vocabulary. And then we need another dictionary that's going to go essentially backwards, so index to words. Making sense so far? We're asking, what does the NLTK corpus words do? Right. This is a large amount of text. We can actually take a look at this. The words inside here. Oh my God, live coding. So PM denies knowledge of kickbacks, blah, 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 blah. If we actually see the length, I think we see the length of the text. Yeah, this is basically 700,000 words. The vocabulary, I think, is 30,000. One of the things we'll experiment with a little later on is actually sort of changing the vocabulary size by making, by lowercasing everything. So because essentially, if you've got, in this case, if you've got if with an uppercase I and if with a lowercase I, those are two separate vocabulary tokens, which effectively kind of mean the same thing, except that maybe one of them is at the beginning of the sentence. But effectively, you can reduce the vocabulary size this way. And one of the most interesting things is what happens when you chop words. So, for instance, if you were to do stemming, which essentially means taking, if you've got a particular word, such as I don't know, let's say computer or something like that. You've got compute and or there are basically you can split up words, or like dancing, for instance. Dancing. You can essentially split this up into two separate words, and this kind of interplay between words that are quite common or endings that are quite common can actually help a model understand things better. But this is a little bit more advanced that we can get into later on in time. So let's actually just sort of dive right into what it is that we're going to be doing. We have our vocabulary. The task that we're going to do to essentially train these word embeddings is essentially going to be, the task that we're going to do is given the two previous words. So for instance, in this text, given the two previous words, what is the third word? That's what we're going to do. This is called a trigram neural language model. And what we're going to be doing is essentially given when and 40, we're going to predict what the next word is. And we can see this in the data set over here. So for instance, when we create this data set, it should be pretty fast. And we look at the first example. Yeah, so this is basically the context is just going to be a list of two words over here. Target is just going to be the word that comes afterwards. And then we're just going to turn these into the associated IDs for these. And then, and the point of this is essentially given these two numbers, predict this number. Again, like the previous time, we need to collate these if we want to batch them together and that sort of thing. And we can just simply do this quite easily by creating a tensor and stacking them. So here's an example of what this looks like. Oh my gosh. The batch size is enormous. So if we change this up a little, we set the batch size to 2, for instance, then we're going to have these two previous words, and then these are the 2 target samples that we want, that we're looking to obtain from the model. And this is the most interesting. This is where the architecture of this comes into play, because essentially what's the input to this is going to be, let's take a look at the architecture that's happening. We're taking two words and then we're trying to predict the third word. And what's happening here is, given an embedding of say 0, 1, 0, and then another embedding 0, for instance, all these connected up, that sort of thing. What we need, what we're going to do, though, I'm just going to go through the model and then we're going to understand little by little what's going on. We have exactly the same thing as before. We're just casting these vectors, these one hot encoded vectors, into essentially another series of vectors over here. So this is the embedding layer, effectively, just like what we saw before. So these are our embeddings effectively. We now have two vectors that are the size of our embedding dimension, which when we define our embedding dimension, we're just going to define this as 100, for instance. So here, so each one of these is a 100 dimension vector. These are effectively vocabulary size. So if our vocabulary size is also 100, I think. Len vocab 97. So these are 97 that's the dimensionality. And then what we're going to be doing, we are defining a linear layer. So remember linear from last time. This essentially, this is just a matrix. This is just a matrix containing essentially a series of connections, much like the line that we were studying before. These are so a linear layer simply involves taking your point in space, right? This 100 dimensional vector is essentially a point in 100 dimensional space, and the linear layer, the first process is essentially multiplying by the contents. So essentially, there's a matrix inside this linear layer that describes a transformation from an input space to an output space, and that's effectively a rotation. That's what's happening. So you have a point and it's being rotated in space. And then the next thing is you apply a bias. And then the bias, similar to what we saw before, is essentially just like if we have AX plus B, the A is going to be a matrix that specifies the dimensions. And then B is just going to be a vector that is applied to say, to apply a translation in space. So essentially, when we're applying a linear layer, we're doing a rotation and then a translation in space, and that's what's allowing you. What's allowing information to flow a little bit, because these are all learned parameters effectively. And so what we're seeing here is the context. What we're doing is context size times embedding dimension. Now, when it comes to, we're gonna figure out what this all means effectively. What we're doing is the context size, which is 2, we're taking 2 words as context, times the embedding dimension, is then going to a dimensionality of, is then being reduced down to 128 dimensions. So this is essentially taking two vectors, it's taking 2 vectors of size embedding dimension, which we have right here. Right here, these are our 2 vectors of embedding dimension, and then they're being reduced down to they're being sort of concatenated as part of the same input, and then being reduced down to a 128 dimensional vector. So essentially, this is what we have over here. This is what's happening. We have our first linear, so linear 1. Linear 1. It's happening over here. And then the second linear is taking the 108 dimensional vector up to vocabulary size. All right, so here we have 2 times embedding dimension, which is 100, down to 128. And then we're taking a 128 over here up to the vocabulary size. And vocabulary size is 97 over here. So the output is going to be a vector that is of size 97. And the interesting thing here is that this is actually the really interesting part, because we need to figure out how to train something like this. And what this is, what the 97 is telling us, what this last layer is effectively telling us, is which one of the 97 words is the most likely one to happen to occur after these two. So all the learning is kind of happening in these sections. These are the sections where our parameters are learning. Over here and over here. This is what's happening. And question would be interesting to see how prediction accuracy changes when increasing the context size. Yeah, we can actually test that out just now, because essentially this thing trains fairly quickly, and it'll be it is actually quite interesting to see how this thing changes. So a way to think of what's happening here is essentially this 128 dimensional. So this last linear layer is essentially taking the sort of reduced, compressed version of the context, right? Essentially, all the context is being boiled down into this one vector that is of dimension 128, and then it's being cast to the vocabulary size. And what this looks like is essentially you have a single vector over here, a single vector that is of size 128. 128. So this is this vector over here. It's right in the middle. That's this vector. And then what you're doing is you are multiplying this vector by a 128. 128. I can't write. 128 by 97. And effectively, this could be seen as a 1 by 128 matrix when it's just a vector. So this is this linear 2. So linear 2. And if you remember what was happening before, similar to what's happening here, we're essentially trying to select, we're saying, okay, which one of these vectors is actually most similar to this vector? You see, when we're doing vector matrix multiplication, what's happening is we're doing essentially a whole bunch of dot products inside. What we're doing is we're essentially saying, okay, how similar is this vector to this vector, and how similar is this vector to this vector? And we'll give an example, because essentially when we're doing I'll give an example of dot product, and then we'll actually see how this applies to this vector matrix multiplication. So for instance, if we have a vector, say 1 to -1, and we have another vector 1, 3, -0.5, right? When we do the dot product of these, we're actually doing just sort of 1 times 1 plus 1, 2 times 3 plus -1 times 0.5. And This is going to give us a particular number. This is going to give us 1. This is going to give us 1 plus 6 plus 0.5. This particular case, which is going to give us 7.5. And if we take a vector that is very different from this, say for instance, we have a vector negative 2, negative 1, and 0, for instance, this is what this is doing is essentially, if we do the dot product between these two, this is going to be 0. This is going to be -2 plus -1. So this is minus another 2, and then this is plus 0. So it's going to give us -4. And here what we're getting at is that the dot product is telling us how similar these two vectors are. And the interesting thing is this vector over here. Oh gosh, this vector over here, we're actually doing exactly this when we're casting when we're doing this last linear layer. We are essentially taking this one vector, and then we're comparing it to every single other vector inside every single other row. And then what we're receiving at the end of it is a series of dot products. The last vector that comes at the end of this as a result of this operation is one that contains all these dot products together. So 7.5 and -4, and so then all the way down. And this is the really interesting part, because we're essentially trying to compare how similar is this vector all the way down. And finally, the result is essentially a distribution over the entire vocabulary of our a distribution over the entire over our entire vocabulary for the probability of the next word. And this is what this is all that happens, because once we take the output of this, then the model has finished. We've essentially done our part over here. And then the only thing that we need to do is essentially train the algorithm to make it as likely as possible to increase this dot product right here, and decrease the dot product for all the other words. So essentially, if for instance this is the correct word, then we want to increase the dot product. This dot product needs to increase, whereas all the other dot products essentially need to decrease. All of these need to decrease, because what we're trying to do is increase the probability of that word being chosen, because that's the word at that particular index. So we can see right here, we take our context IDs. Once we pass from a particular batch, we get our targets. We convert, we pass these to whatever device we're using. So for instance, we can use either the GPU or the CPU for this sort of thing. Same as before, we set the gradients off to 0. And then finally, we just get our predicted vocabulary scores. And then afterwards, the loss function that we're using here is called the cross entropy loss. So all this is doing is emphasizing when a particular, it's essentially saying, whatever index you chose, if the correct word is this word, then you're what my objective is essentially to give you a score that says you should increase this score and everything else should be decreased. That's all the cross entropy is doing, because all it's doing is simply saying, it's just simply choosing that particular value and then setting everything else to 0. So if we try and minimize this value, then what we're going to do is increase the dot product in this case for that particular word. So once we set these down, the model is defined. We can set this to CPU, for instance, right now. It won't be super heavy. And then setting up a single training step will give us a particular loss. So this is essentially for every single element in the batch, we're then saying how how bad is our prediction? How far is our dot product from what we expected? And then if we train this enough times, so for instance, we should see this go somewhat. It should be training at some point. What we're doing here is we're just using a batch size of 2 and iterating over all the elements inside our data, which is this data right here. And we're just choosing all these words. We're just training the algorithm to predict the next word. Colab seems to have crashed, which is really unfortunate. Yep. This is such a shame. Okay, we'll restart the environment. So we have a question. Would then synonyms have to be near each other in the vocabulary to make accurate similarity calculations? So one of the interesting properties of this is that synonyms are close to each other in this space. Because what happens is when you're trying to predict the next word, so for instance, if in the sentence, I like cats and dogs, that we have over here, what it turns out is that given the context of I like cats and dogs and pigeons and all these sorts of things are are sort of grouped together, and they because they are all like quite likely to be chosen next, and so that's a property of what happens after doing a lot of language learning. And what about words with several different meanings? So, oh, you mean like polysemy? Okay, I understand. So these are really good questions, because these are exactly the sorts of things that that context tries to address. So, for instance, if you've got a single word, of course there can be different meanings. So, for instance, you've got apple, the company, and apple, the fruit. You have butter, the sort of the stuff you put on toast, and peanut butter, the stuff that's made out of peanuts. Lots of words on their own actually have have lots of polysemy, and the problem is that how do you represent these? This is actually something that isn't addressed by this model, because essentially these words are only a point in space, and they're not 2 points and that sort of thing. So it actually has a lot of trouble. You will not be able to distinguish words that have multiple meanings. Really, what will happen is something like this. You'll have like your space. I don't know. Like, imagine this is your space, and you've got apple over here. Apple over here. You might find it like that apple occurs more frequently in the text as a fruit as opposed to the company, in which case you will find other things like pear over here, and then companies like Tesla will be over here, and other things like General Electric. Apple might like eventually make its way over to someplace in the middle, but essentially it's sort of somewhere, the meaning inside is somewhere in between fruit and a company, or whatever other meaning that could be given to Apple. So this is a little bit of a problem with this kind of model, and it's actually the issue that's addressed with models such as BERT, where you have the meaning of the vector representation given to a word at the end of this process is actually not just dependent on the word itself, it's dependent on the context. So for instance, if you have the sentence, here we go, Apple rose 500 points today. This sentence here, Apple has clearly has the meaning of the company, but you can't tell this by the word itself. If this was blacked out, then you would have no way of telling that. And so the way we solve this is by essentially including the context. Whenever you're computing this representation, you're keeping all these as well whenever it comes to computing that context. And then that word essentially is imbued with all the representation of the surrounding words as well, which then helps disambiguate this. So hope that answers the question. Here we go. And yeah, let's see if our model is actually behaving as we expect it to. Because it would be great to have this trained. Because essentially what we can do here is we can just keep generating text. We can just be like, okay, given the two previous words, generate something. Yusuf, you just raised your hand?
Yeah, following on from that same question, I don't know if I misunderstood, but how would the model know how many words to include in the context, or would it include the entire sentence or the entire text when it's processing that one word? I don't know, might be a silly question.
So really it comes down to, so for instance, a model like this, as we've described before, the architecture itself is sort of set in stone for only taking in two words. As in, if you try and feed it like one word or two words, you're going to have to do something weird, because essentially you're either, imagine you only have one word. What you're going to have to do is essentially set this to 0. Like one of these is going to have to be set to 0 if you've only got one word. And if you've got 3 words, then you can't do anything. You're just going to have to take 2. Other models are more flexible. So for instance, BERT is a model that uses an attention mechanism, which we're going to take a look at next time. And this essentially is a way of aggregating multiple words together. You could imagine that one way of aggregating words is actually, if you have, say for instance, your sentence, it could be any sentence. Like let's imagine it's 3 words long. I don't know, like apple, apple is great. Suppose there's a future in which that is the case. He says an iPad in hand. So here we have 3 vectors. One way of doing this is, imagine you take the word embeddings for each one of these vectors and you just sum them together. Here you can essentially take any context length and then just shrink it down into one vector and then do your computations on that. The problem is that summing vectors together, like summing word meanings, is essentially the same thing as saying, like, for example, oh, we've got Tesla, and then like is over here, or we have Apple, for instance, we have is, and then we have great, which is someplace down here or something, great. And then you sum all these together and you get some Frankenstein vector that happens like right in the middle here. Because once you sum all these together, and then this meaning is actually like really weird. Like this is someplace in the middle between apple is and great, which sort of doesn't make sense. So when it comes to like aggregating these words together, you have to get kind of clever and figure out like how and try and figure out a way that makes sense to the model. Because if you're summing vectors, if you're multiplying them together, if you're taking the maximum value between them, then it's really awkward to think about. And really, a lot of experimentation comes down to this, because there might be representations that work quite well, but in general, summing vectors doesn't really work.
Right. So we use other aggregation methods essentially.
Yes. So
like what we'll learn with BERT.
Yeah. So BERT actually does a similar thing with like these essentially aggregating things together with just summing. The thing is, in this particular case, each one of these vectors is going to be multiplied by like 1/3, because there are 3 vectors. Yeah. So so the weighting is essentially the same. The thing that BERT does very, very well is through what is attention, essentially say, okay, well, the is actually quite important in this case, because is actually sort of giving us the indication that apple is an entity as opposed to the fruit. So even though is a sort of an interjection in this particular case, it's actually really valuable in the sentence. So hopefully Bert would essentially be like, oh, this is not 1/3. This is like 1/9. Like this, the importance of this word is actually really, really high.
Did you just?
Oh, not 1/9. Sorry,
like
1/1/, I don't know, 0.9
would work.
Yeah, 1.2 or something like that. It will be the score would essentially be 0.9 over here to indicate a high score, and then everything else would be a low score. So I mean, great would be 0.4 or 0.05, and then this would be 0.05 or something. And so the representation, once you sum all these together, then the weighting actually tells you a lot of information, and this is what's happening.
So if you had something like the apple is great, then in this case, apple. The and is would be quite important because they're telling you that apple is not a definite, is not like a proper noun.
Precisely. So for instance, you would actually be able to say, you kind of make judgments on this because this is why context is like so important in this particular case. And this is how the algorithms such as BERT manage to do polysemy fairly well. BERT is by all means not a magic bullet. It is very good at what it does, but it's not all powerful. It's just the current best of what we have right now. Venus asks, the same sum could be reached with completely different sets of words, though. Do you mean sort of the same sum here? You're welcome to unmute if you want to as well. It might just make things easier than typing them. But I'm guessing what you mean is if you've got a different set of words, such as, I don't know, peanut butter is something, then you could get this sum as well, these same coefficients. But effectively what you're doing is you're adding different vectors together. The underlying vectors that are peanut butter and something else are inherently different, and that's what's happening. So let's get back to our model over here and see how well it can train. Right. So here we can see the training loss, for instance, is going down, which means that over time, our vectors are actually, the model is getting better and better at predicting the next word in particular after going through the text. So we started at around 200. This is now going all well below. And these are just the number of epochs that we're using. So we could stop this at any time. Let's actually stop this right now. So for instance, with just basically no training whatsoever, as soon as this stops, I think there's an issue with TQDM when you're trying to do too many things at the same time. Please stop collab. Oof, this is crazy. Okay, we stopped at a particular value. And we're going to do an example here and see what the model predicts. So for instance, in our text, one of the things that we want to do is when and 40. Right, these are two words. What we're hoping is that when and 40 is that the output of the model is going to predict like the word winter or winters. Winters. That's what we want the model to predict. And if we give it, yeah. So basically, here what it's saying is the most likely word to come next is winters, but the next most likely word, the next most similar word that we were seeing here. So for instance, the vectors, the ones we were seeing here, the vectors that are next most likely to be chosen in this whole list of vectors, in the vocabulary, would be specified by, the next one would be be, the next one would be more, then when, then thy. And the interesting thing is that this is a form of classification. We're essentially classifying out of the entire vocabulary, which is 97 tokens, which one of the 97 words is most likely to come after when and 40. And thank goodness, after the training, winters is the next one. But you can see that if you give this model enough time and enough context to train and that sort of thing, then it will actually do fairly well. It will learn these the representations fairly well. So we can actually explore to try and train on like a much larger set of data. So this is why we have this huge book corpus before. Essentially, we can even try with different word combinations before we try this. So for instance, treasure, like when treasure, or let's see, we can actually try. What shall we try first? So we increase the context length with the model to see how it behaves. Shall we test some other words? Shall we just try with like a much larger corpus, see what happens? If anyone wants to unmute and say, they're welcome to. The whole idea is this is a little bit more interactive, to be a little less like homework sort of thing. Benas asks, the same sum could be reached with completely different sets of words. In inference, all words must be present in vocabulary, right? We can't give it unseen words. So if you think about it, what is an unseen word is essentially a word that isn't in the vocabulary. And so it isn't in you cannot make a one-hot representation of that word because it isn't in the vocabulary. And so there is no embedding that can represent it. And this is why you can't have like out of vocabulary words, or characters that or words that aren't in the vocabulary just have no meaning to the model whatsoever because they haven't been trained in any way. One way to get around this is, for instance, the character embedding model. If instead of embedding words, you embed characters, then you're able to you're able to sum things differently. A word might still make sense. A completely new word might still make sense if it hasn't been seen by the model, if it contains a certain set of characters. But that's another test. That's another thing that we can try. I mean, for instance, we could actually even split this by characters and then see how well this works, which would actually be quite interesting. But essentially, let's take a particular word. So I don't know, proud, and let's take proud and 40, and let's see what it predicts. 40 winters. So it still predicts winters as the next most likely, but the tail distribution has changed then after. And if we change something from like proud tottered. This here essentially, because there's such little training data and we trained it for so little, it's basically still very, very much a baby language model. But let's try with a larger training set. Let's use the big word corpus, see what happens. And again, if anyone wants to interject and ask something, go ahead. The vocabulary needs to be set. So now the length of our vocabulary is 31,000 different words. That's a huge vocabulary. If you imagine what the model is doing at the end of it, the model over here, right towards the end, this vocabulary, the end matrix is taking a 128 dimensional vector and then comparing it to 31,000 other vectors and then seeing which one is the most similar to it. And then it's ranking those by order and then saying like, okay, well, word number 5,000 out of the 31,000 is the most likely one. And that's what we're going to do here. So if we create this data set, which should be fairly fast if Colab doesn't decide to die on us again, which it might have. Colab, please. There we go. So here we're still using two words of context. We'll collate these samples together. We can set a larger batch size, say of 16, right? So the input to our model is this. These are our 16 different samples. Each different number has a unique embedding, effectively. And then these are our target words. We define our model again. It's exactly the same thing as before, only the vocabulary size has changed, which we will specify over here. And then the final layer, vocabulary size again, specifies this part. Define it. We'll set it to CPU, see how it behaves. Here's an example of it training just to see if it's good. And this should take much, much longer, I suspect. Again, Colab is acting really, really weird, which is a real shame because we can't actually see what's going on, which is quite frustrating. We cannot see train. Yeah.
So what is TQDM doing?
TQDM is just this progress bar.
Oh, okay, right, yeah.
Nice
yeah, P bar is the right, yeah.
Yeah, because if not, we're basically just running a for loop and we can't see anything.
Yeah.
But at this point, we're exactly doing that because Colab isn't collaborating. Oh, this is so annoying. You know what? We're just gonna like restart the environment like this because I definitely want to see this train. Right. Okay. So here we go. This is the tricky thing because essentially the model is trying to learn what's going on here. We could actually inspect how the loss is going if we cancel this. Oh no. Let's create a new, so P bar 2. And then we're just going to update the description with a particular loss. It's just loss. So if we reinitialize our model, right, we can see the loss is at 10. This is a per batch. And what we're hoping is that over time, this will go down as the training keeps going. Of course, because this is a larger model, or not a larger model, actually it is a larger model because the embedding dimension is, the vocabulary size is a lot larger. This is going to take longer to train. But as it's seeing new words and it's being exposed to all the new vocabulary, over time, this will need to get better and better for each word. It'll be interesting to see how well this works. But in essence, imagine we canceled this right now. We cancel this right now, and then we could actually ask it, like, for example, if we said apple is Erica. So here right now it's predicting bad tokens, but effectively if you ask if you train this for long enough on a particular corpus, you can imagine that it would actually get pretty good at predicting the next token, and the embedding that would represent those words would actually be a meaningful semantic unit that would represent that could effectively represent those words, useful for a particular computer, which is something that we didn't have before. This is which is actually kind of cool. So personally, I want to see if this goes faster on the GPU. CUDA, by setting it to CUDA. Let me know if setting the GPU over is something that you would like to learn more of, because this is actually, it takes a little bit of fiddling to figure out how to put things on the GPU. But just to make sure everything is good, that we get a particular loss. And if we train this, see how well it does. Oh, wow, it's much faster, much, much faster. So instead of 30 minutes, it's going to take 4 minutes, which is great. And we can just let it keep running. we can actually try and increase the speed even more. It's unfortunate in Colab where we can't see the GPU usage of a model. But what we can do is hope that the GPU is not saturated. And we're actually going to increase the batch size to like 64 instead of 16, and then see how that goes. Because essentially what we want is to try and get as much information in there as possible. Let's see. Yeah, 1 minute. 1 minute to train. So here what's happening is the matrix multiplications inside the GPU, because the GPU is really, really fast at doing matrix multiplications. And essentially, as you increase the batch size, the size of those matrices is increased. And because the GPU is so good at doing these matrix multiplications, the ultimate bottleneck is essentially the transfer from CPU to GPU. So if we have our data in the CPU, the limiting factor is essentially how fast can we transfer that data over. And if we set that, if we increase the size of the batch, then essentially the overhead time between the GPU making that matrix computation is reduced in comparison to the size of the data, in comparison to the time that it takes to transfer data over, which is why it seems to go faster. And it's great to see that it is going faster, because essentially we can, once this is finished, once it's completed an epoch, we can then see how well this model is doing and how well it predicts the next word. And we can actually play around with context size. How is everyone doing so far? Do we have any questions on like the model, or how perhaps how these embeddings interact with each other? How is the training procedure? How does the GPU work? Any question whatsoever? This is definitely the time to answer it while we're just playing around with things. Because ultimately we've defined our own model. We set out to solve a task, and we're solving it. The loss is going down essentially. The model is getting better and better at figuring out what the next word is. So for instance, if we cancel this right here, we stop it, and let's check back in to see how well this is doing. Apple is, oh.
Yeah, I got, sorry to interject. I got that exact same thing. I was about to ask about it.
Yeah, this is
when I ran it with CUDA rather than CPU.
So what this is telling us is essentially the expected object of type CUDA got device CPU for argument in index. So this is saying you gave us a tensor, right? Can either live on a CPU or on the GPU, right? So what we're doing in the training procedure, right, which is actually an important part. So for instance, when I set the model to live on the GPU, oh gosh, when I set the model to live on the GPU, the weights inside of this model are living on the GPU, but then the data that remember the data loader that we defined is actually still on the CPU. And when we set the training step, so for instance, whenever we're calling batch, we obtain the tensors from the batch, and then we actually send them to the GPU by using this to command. So for instance, we do context IDs to the device. So here I'm basically grabbing the device, which is CUDA, which is the GPU, and I'm sending the vector over to the GPU, and then afterwards I can then do the computations. So every single vector has to live on the GPU before it does the computation, and that's what we're missing over here. So for instance, in order to solve this, we then just need to say to CUDA. Sorry a second, guys. I'm just going to pause this. Stop video a second. The joys of Zoom life. So once we set this to CUDA, then our data is then moved to the GPU, and we can see. So Apple is full stop. So this is really interesting actually, because or the and are actually plausible next words to is. If we use Apple the, like what would you expect? An interjection would be Apple the company, Apple the something, Apple the. If we say cats and the, so I think what's happening, thinking out loud what's happening here, I think the model, well, first of all, is undertrained. The model doesn't actually know what's going on. And second of all, the is also quite a popular word in the corpus, probably. And that means that it's a vector that is probably quite, if you have a word that you're trying to predict and it's very frequent, then that's something that you maybe need to take care of, because it's going to mean that the words that it might be predicted more often than not, and it's essentially sort of a class imbalance, because we're doing classification amongst the entire the entirety of the data set, entirety of vocabulary. Sorry. We can actually just sort of keep training this. I want to see how far we can push the model. One thing I want to do is increase the context length. So let's put the context length to 4, for instance. Yep. Oh wait, this is not going to work actually, because yeah, this is very hacky. This is 1, 2, 3, and 4.
Do you have to do that for context as well?
I have to do that as well. I have to do this here. This should be fine. There is an error somewhere. Did I delete something? Oh my.
You're missing a square bracket. Second word to IDX.
Second,
the end of that.
Second word to IDX.
Has only one square bracket closure.
Oh yeah, yeah, got it.
And same for the next one.
Same for the other ones. I can probably copied that wrong. This might be good. Just check. Yes, all good. All right. Again, question. I would love to learn how to utilize the GPU to a maximum, tinkering with a number of workers, batch size. All right, yeah. So this is one of the most interesting things, and it's really addictive to try and optimize the GPU accordingly. The way I do it is by using PyTorch Lightning. So PyTorch Lightning is similar to regular PyTorch, but it's actually designed to have like a few helper functions and that sort of thing. And one of the most interesting things that it does is it has a batch size search algorithm, and basically it increases the batch size until such a point that it maxes out your GPU's memory, and then it just uses the one that uses the maximum memory. So right now, data set at 0 is going to be huge, most likely. Why is this taking so long?
So, I was going to ask, is the training is this code running on our own machines, or is it running on the server? Because for some, right, yeah, because for some reason, I'm running the final training cell, and I'm already done like 20 epochs, and it's taking about 10 seconds per epoch.
Are you training on the large corpus?
Yeah, on the whole corpus, really? With 2 words per context. Two words in the context.
That's actually that's really fast.
Using CUDA. And it was quite slow. It was very, very slow on the CPU.
Yeah.
But yeah, it seems to be going much faster than it is there. So yeah.
So are you running on the local environment?
How do I know that?
I think up here you can actually see like connect to local runtime.
Yeah, so it says both. It says connect to hosted runtime and connect to local runtime.
Okay. So context needs to be set to 4. We use CUDA. This should run. Yep, correct. And so in my case, my time takes around 1 minute for 4 words of context with the big corpus.
Okay.
Another thing that we can play around with to see if this goes faster is, remember last time where we had the learning rate? Right now, let's take a look at learning rate. It's around it's around 1,000. It's 1/1,000. We can actually set this to 1/100th, and let's see what happens there. If we set this to 1/100th and set it off to train, let's see, it's going down much faster, much faster. Is everyone actually working on the collab, by the way? I'm actually really curious because I can only obviously see myself. Yusuf, you seem to be working on the collab, but whoever's working on the collab, just sort of like do the clapping emoji, and then just so I can gauge who's working on it. Yeah, Gabor's working on it. Nice. Okay. Could you go over once again why we use exactly 128 dimensions for the vector between the 2 linear layers? The reason we use it is just because it's a design decision. We really didn't. There's no concrete reason why. This is what's called a hyperparameter, and there is no way to really make a good decision on it, other than sort of assuming that 128 dimensions is a good number for expressiveness inside the model. And essentially, if you think the model could, if the data is like detailed enough and expressive enough, you can increase that number to say 1,000. But of course, that comes with extra compute power.
I think I might know why it was taking 10 seconds. I just refreshed the page and the batch size reset to 64. I think it was 512 before.
Oh, okay.
So
yeah, so
that have been it?
Yeah, that's way better then. Like the thing is, 512 just means that you are doing like things in like huge batches, just going like, you're just big batches at a particular time.
But is the training quality still the same? Like, is it just free performance or?
So this is, so for instance, a larger batch means that it's a more informed decision. In general, it's a good idea to have as large a batch as you can, because it means you are increasing the efficiency of the training process, and you're passing more signal to the model. If you just do 1 sample at a time, then you might be able to go fairly fast, but the signal ratio is quite low because it's just 1 single sample per step. Whereas with 500 samples, that's like 500 samples making a decision on how those parameters should go. I'm actually really curious. I want to increase this to 1,024, see how fast the batch goes. And I'm going to reduce the learning rate by half. Oh wait, but I can't do that without resetting the model, so it's not going to do that. Yeah, so much, much faster. Does anyone have any observations, like any experiments that they're running right now that sort of are interesting with their notebook? So this thing's running. Yeah, that's fine. And then finally, I'm actually just kind of curious what it says here, cats and I. We say I like cats and the hit. So predicting a lot of interjections.
I wonder how far away dogs is in that list, in the predictions list.
Yeah,
how many predictions does it make anyway?
It's predicting over the entire vocabulary. So
okay.
Yeah, because it's ranking every single vocabulary element in vocabulary. We can see how far this goes. So here it says I like cats and other says I like cats and people. I like cats and you. What's a very typical sentence in English? We'd be like, the weather was. We need a fourth word though, because our model isn't flexible. The current weather is the very, yeah, these are very sort of generic words. And if we just like increase this all the way down. Miles says, I'm not able to find the notebook. My network is overloaded. Would stop word removal help here? That's a good question. That is, so stop words in this case, I don't think would actually help. I think because essentially here we're using a context length of 4, these are essentially sort of, these 4 words are set in stone. Artificially weighting them could be done, but you have to think, what does artificially weighting mean? You kind of have, like when it comes to the embeddings, you kind of have to say, okay, well, I guess you have to weight them based on how frequently they're used. So sort of inverse, this is what's called inverse document frequency, where you essentially say how frequently they occur in the corpus. So the could be scaled down, for instance. But this is, again, this is a little bit of an artificial measure. I think that the best solution is actually just to train effectively. Has anyone tried how far this model can be pushed? 2048, for instance, that kind of batch size. We set the model to learn, model to CUDA, and we set this off.
So yeah, I'm just on 20 epochs out of 1,000 now. I'm wondering how long to give it before I stop.
I mean, you can resume it afterwards. The model stays.
Oh, you can?
Yeah, you can stop it.
Also, if okay. Like because if I stop and then play, it just keeps going.
The model is essentially captured. It's a variable in Python. Like these are numbers changing inside. So you can actually change it as much as you want, really. Can you, I would be actually really curious to see what the predictions of your model is. How much was the loss?
I'm just trying to find it. 10.36.
Okay, that's still quite high, I would say.
Mm.
Any other questions by anyone? Or sort of curiosities about what happens if we try something? Because I think soon enough we might actually call it once we're done. The next session will be on attention, and we'll essentially be doing actually quite a similar task to this, a language modeling, but we'll be able to use variable length sentences as opposed to just always having either a context length of 2 or a context length of 4. And even though this attention is a very general algorithm, we're just going to use it for this specific case, and you can use it for loads of other things. You can use it for images, for instance. There's a field that has been popped up recently. Like right now, we're using words. We're giving individual word IDs. There are associated embeddings, but pictures can also, as long as you can represent it as a fixed vector length, you can actually consider any length you want, and any sort you want, words or text or to music or anything else. It all just needs to fit essentially inside the model and play nicely. Right. So this thing is just still going on. I'm kind of curious. Let's see how this performs. The current weather is element, depression, velvet, streamlined, east. Actually, is here we're relying on the text containing a large amount of information here. Yeah, I think we've kind of concluded this session. How has everyone found that so far? I saw some language models generating continuing images. Is it the same process, but instead of words, the embedding represent RGB values? That is correct. That's exactly what's going on. And it's really interesting to see how that works, because you essentially have the image is just essentially flattened out. The image is just flattened out into an array like this. And you can have attention that you can have your architecture can pay attention to specific sections of the image, for instance, at a particular time, so that it keeps some sort of spatial coherence. But effectively, what's happening is you're just adding a little extra bit to the sequence, and the model is just sort of predicting it one word at a time, one pixel at a time, and that's it. Nothing more. So really, these models are quite flexible. An interesting fact, for instance, when language models were still sort of trying to figure out what the best way for the representations were, people used convolutions over text. People used to use convolutions as a way to essentially have your word embeddings over here. I'm realizing it's very difficult to see these. You had your word embeddings, and then you would essentially pass a convolution over each one of these. And so on. And then these representations would then be bubbled up to the next layer, where all of these representations would condense up. So these convolutions were used in text as well before, and essentially all these architectures have different advantages and disadvantages. Ultimately, what we're finding is that there are a few general paradigms that perform really well at certain tasks. Attention is one that performs quite well. and convolutions also perform really well. There's really good inductive biases there. And then there are a whole bunch of other ones like feed-forward layers that are very, very general for these sorts of things. So yeah, I think we might call it there. Any last questions? And this is the last chance. I think next week we'll be taking a look at attention, and we'll try and do the exact same problem, but we'll design our own attention mechanism, which is really exciting because this is actually putting us in a position to work towards the final goal, which is building the BERT algorithm from scratch. And the idea here is not to obtain an algorithm that works supremely well, because we don't have as much computation as Google does, which spend like thousands and thousands of dollars to train it. We just have a Colab notebook. But the objective is to be able to understand what's going inside these models in such a way that if you want to, you can modify them as you wish. And in general, inside every single PyTorch model, you will see an init with which defines certain classes, certain layers and that sort of thing. The forward, the train step where you pass information to the GPU, the training, the loss, all these sorts of things are things that you will see. And in general, you can map out the architecture just this way. So the point of these workshops is to tinker inside these models and to figure out how these things work, not necessarily to get the biggest number ever. However, getting a big number means that the outputs are good, and it's always good to see that. But the objective is to make sure you know how to train, to figure out what's going on. So again, like whenever there's something that you have a doubt on, just let me know. All right, we'll call it there. Thank you everyone for coming, and I hope you all enjoyed. There will be a feedback sheet if you want to put it in the Discord, and it would be great to get feedback on this. It certainly lets me know, and I'm keen to hear if you thought this version, this kind of style of lecture was better than the previous one, which was a little bit more sort of exercise focused, and here it was a little bit more dialogue, a little bit more trying to figure out how to code something and what the inner workings are with a few more questions. Please let me know. It's the best way so that we can make this as best as possible. So without further ado, I think we'll call it. Bye everyone.
I'll just so yeah, thank you for the session. I'll just put I'll put the link in the chat just now as well. So in the Zoom chat, so feel free to catch it just there. And it will also be on Discord. As this is the link to the feedback form. There we go.
The feedback form, yeah, it'll be great to get feedback. Thanks for the help, Yusuf, by the way. Big shout out.
No bother, yeah. Yeah, it was great. Because I personally never studied this kind of stuff, so it's great to get an idea of it.
I hope it's coming across efficiently.